Hello everyone. So last time I could not actually record all the problems that I wanted to go over, and I didn't do a good job on going over problem 33. So now I want to go back and start with problem 33 and try to finish the rest of the problems at this point. So problem 33 is about the Compton effect. We have a 0.160 nanometer photon that strikes a free electron in a head-on collision and knocks it into the forward direction. The rebounding photon recoils directly backward. We are asked to use conservation of relativistic energy and momentum to determine A, the kinetic energy of the electron, and B, the wavelength of the recoiling photon. And we are asked to use equation 5, which is here, the relationship between momentum and wavelength, but not equation 6, which is actually the Compton effect formula. So we can't use equation 6 to solve the problem, but we can of course use it to verify our results. Okay, so let's try to go over this. So this is problem 33. So we have an electron that's just sitting here. A photon at a certain wavelength is coming, hitting this, and then just going directly backwards, right, with some, let's say, lambda prime. So lambda prime is larger than lambda. It gives some of its energy, and that energy leads to some velocity of this electron over here. Okay. And in part A, we are asked to find the kinetic energy, and in part B, the wavelength of the recoiling photon, I believe. Yeah, the recoiling photon. Okay, and we are required to find, use relativistic conservation of relativistic energy and relativistic momentum. So let's write these down. So conservation of momentum. So initially our photon, momentum is a vector quantity, so we have to choose a direction. I'm going to choose this direction. It's positive. So initially the momentum, the photon has a positive momentum. So that's h over lambda. And the electron has no momentum, so that's our initial momentum, just h over lambda. The final momentum is the backwards momentum of the photon, so this is minus h over lambda prime. Now it's negative because it's going backwards with respect to our positive direction, and the electron is going to be moving forward, so that's going to be plus gamma mv. Right? I'm not putting any subscripts here because, well, there's only one thing with the mass, and with the velocity it's just the electron. Okay. Conservation of energy. So the photon's initial energy is going to be just hc over lambda. Now the electron is at rest, but it still has the rest energy, so this is going to be mc square. The final energies is hc over lambda prime. This is positive. Energy has no direction, so it's always a positive quantity in this case, and the electron is going to have the energy gamma mc squared. Okay. So these are two equations, and we have two unknowns. We don't know lambda prime, and we don't know gamma, or equivalently we don't know v. Right? If you know one of those, you can find the other. So this is two equations for two unknowns, and in principle you can solve it, though it might be a bit complicated to solve this. So one way to solve these equations so in part A, they're asking for kinetic energy, right? So the kinetic energy, which is equal to gamma minus 1 mc squared. So what's this? This is what they're asking. So we essentially need to find gamma, or gamma minus 1, something like that. All right, so we need to eliminate lambda prime, and one simple way to do that is to multiply this equation by c and then add these side to side. And this has negative hc over lambda prime, and this has positive hc over lambda prime. They are going to cancel, and we're going to end up with just gamma. So this is 1, let's say this is 2. So multiply 1 by c and add side by side. By side. Okay, what do we get then? So on the left hand side we get 2 hc over lambda plus mc square is going to be equal to gamma mcv plus gamma mc squared. Okay. Then we can move this to the other side, arrange things a little bit, right? Yeah. So we can write 2hc over lambda is equal to gamma mcv plus gamma minus 1 mc square. So the first time I solved this problem yesterday, I claimed that this is a small number. I can neglect this, and then this kinetic energy is just equal to that. That's not correct. That's not actually small. It's not negligible. I mean, it is small, but it's not negligible. You make a substantial mistake by neglecting this term. So we actually have to solve this honestly, right? So how do we go about solving this equation? Now we are looking for gamma. Like if you find the value of gamma, we can calculate this kinetic energy very easily. We know the value of mc square. So I want to write this v in terms of gamma, and I'll substitute there and then try to make an arrangement. Okay? And I also make one arrangement in this equation that will make my life easier. And that is going to be, I will divide both sides by mc squared, right, to make everything dimensionless. So I'm going to have 2hc over lambda by mc square here, and this is going to be equal to gamma v over c plus gamma minus 1 over here. Okay? And this is a number I can calculate. So this is just the energy of the photon. This is the rest energy of the electron, and I'm just multiplying by 2. So I can calculate that number. So hc over lambda by mc square times 2. It's actually something I already calculated. This comes to something like 0.0303327, but I will simply call this x. Right? I'll just call this x. And then I'm going to try to solve it, solve this for gamma in terms of x. Okay. Now I need to express this v over c in terms of gamma, so I will actually have an equation in terms of gamma. So gamma is of course 1 minus v square by c square to a half. So if you rearrange this, what you get is that v over c is equal to, let me see, what did I find? V over c is gamma square minus 1 to a half divided by gamma. Okay? Now you take this value, you substitute this in here, and what you get is x equals gamma square minus 1 to a half plus gamma minus 1. Right? So I move this to the other side, take the squares, and so on and so forth. So 1 plus x minus gamma squared is equal to gamma square minus 1. If I take the squares on both sides, this is 1 plus x squared minus 2, 1 plus x gamma plus gamma square is gamma square minus 1. So gamma squares go away, and I get an expression for gamma. So gamma is going to be equal to, I move this to the other side, this to over here, 1 plus x squared plus 1 over 2, 1 plus x. Okay. What I'm looking for is actually gamma minus 1, and if I write an expression for gamma minus 1, let me check my notes here. I get x squared by 2, 1 plus x. And you substitute the value from here into this expression for gamma minus 1. You get 4.465 times 10 to the minus 4. Okay? And when you multiply it by, okay, I'm going to just use this region. If you multiply this by mc squared, gamma minus 1, mc squared, so mc squared is 0.511 MeV, so 0.511 times 10 to the 6 eV. You multiply it by this, you get 228 electron volts. So this will be your answer. A little bit convoluted, so this takes like half A4 to solve this. But writing down the equations is the most important part, right? Because after you write the equations correctly, you can actually use a computer algebra system to solve this. Not in the exam though, right? In real life, you can use the computer algebra system, but not in the exam. In the exam, you need to go through this algebra. It's not too hard, but it's what I call tedious but straightforward kind of calculation. Okay, so for part B, they're asking for lambda prime, and perhaps the easiest way to calculate lambda prime is to use this. Right, this one already has lambda prime. I move this to the other side. I get excuse me. I get gamma minus 1 mc squared, which I already calculated. So from equation 2, I get, so hc over lambda 1240 by 0.160 is 1240 by lambda prime plus something we calculated, 228. Okay, so this gives the energy of the incoming photon in electron volts, and this is just this expression I've written in nanometer electron volt units. So this lambda is going to come out in nanometers, and this is what we already calculated. It's a simple equation. You can just carry out the algebra and solve this. And if I did my algebra correctly, lambda prime comes to 0.1648 nanometers. So the initial one was 160. As expected, this is slightly higher. So as you see that it's not too unreasonable to make that approximation. This is a small change, but it's not very small. It's not less than 1% or anything like that. Right. So yeah, you actually need to solve this problem a bit more honestly. Okay. So problem 38 is an electron and a positron, each moving at 2 times 10 to 5 meters per second, collide head-on, disappear, and produce 2 photons moving in opposite directions, each with the same energy and momentum. Determine the energy and momentum of each photon. Okay. So this is a pair annihilation. We have a pair of electron and anti-electron, positron, and they annihilate each other and produce 2 photons. Let's take a look at this. So I have an electron incoming, and I have a positron incoming. They annihilate each other and they produce 2 photons going in opposite directions. So these thetas are the same, and these photons have the same energy and momentum. In fact, they have to be. This is being solved in the center of mass frame, the frame in which the center of mass of our system is at rest. So yeah, you can't have it any other way, right? Unless the momenta are equal, the center of mass frame, the center of mass will have some momentum that's not allowed, because initially it has no momentum. Anyway, so this is going to have some frequency. What are they asking? Determine the energy and momentum of each photon. So these go away with some energy and momentum, and we are required to find those. And the velocity of the electron is equal to the velocity of the positron, and that's 2 times 10 to the 5 meters per second. So we are to use conservation of energy here, and we're going to use that to find the energy of the photons, right? So the initial energy is twice gamma m me c squared, right? And this is going to be equal to twice hc over lambda. And this is the sum of the energy of the electron and the positron. This is the sum of the energy of the two photons, so these go away, and we can calculate the hc over lambda, this energy, very easily. Well, I actually don't need to write this in terms of lambda. They're not asking for lambda, so I can say this is twice the energy of the photon, right? And that 2 goes away. All right, and to do that, I need to calculate gamma, but this is straightforward, right? Gamma I can calculate from here, and this one is 0.511 MeVs. So you can carry out the calculation. I'm not going to do this. You can carry out the calculation, just the algebra. And then they're asking for the momentum as well. So so this is the energy part. For the momentum, we can use this relationship, right? And so the momentum of our photon is just the energy calculated divided by c. And again, by using appropriate units, this can be done very easily. There is really nothing to it. Right? So this is a straightforward application of the formulae. Perhaps the tricky part is to decide what you're going to use. Trying to use conservation of momentum is going to be kind of useless, right? If you start with the momentum, right? So the initial momentum is gamma MeV minus gamma MeV, which is 0, which doesn't help you. It doesn't help you to calculate momentum of the photons. You need to use conservation of energy, and from that you need to deduce the energy of the photons, which determines the momentum of the photons. Yeah. All right. Okay, so next question is 79. This is almost the same problem, but just reversed. An electron and a positron collide head-on, annihilate, and create two 0.755 mega electron photons traveling in opposite directions. What were the initial kinetic energies of the electron and positron? Okay. So perhaps we can do this remaining part over here. As I said, it's almost the same problem. It's just we have to use the same equations. We just need to. So this is 79. Oh, sorry. Let's switch this. So this is problem 79. Again, we have the same geometry, but this time they are giving us the energy of the photons. The energy of the photon is 0.755 MeV. Right. So first of all, does this work? Can we have two photons like this? Can we actually produce? Is this valid? Right. So is there, because there's a minimum energy for the photons that's produced as a result of this process. Right. So each of these has energy half MeV, 0.511 MeVs. So the photon needs to have at least that much energy. Right? Because they also have kinetic energy, generally the photons are going to have larger energy. If they were just sitting at rest and they just collided and annihilated each other, the photons produced would have half MeV, but because they are actually moving with some velocity, the photons are going to have some additional energy. So the difference between that 0.511 MeV and 0.755 MeV is actually the kinetic energy of the electron and the positron. Right. So well, I already said this. So the kinetic energy of the electron is going to be E total minus E rest. This E total is simply the energy of the photon. Now, strictly speaking, there's two everywhere here, right? So there's twice the kinetic energy of the electron because there's an electron and a positron, and this is twice the total energy of the electron because there's an electron and a positron, and so on and so forth. But I can just get rid of these and think of just one. But strictly speaking, our equations should actually start with twice these values. All right, we write this down. So the kinetic energy of the electron is going to be 0.755 minus 0.511, which gives 0.755 244 MeVs. Okay, so this was the kinetic energies of the electron and the positron. As I said, this is very, very similar to the previous problem, but you can obviously ask the problem in two different ways. Okay. So 43 is what's the theoretical limit of the resolution of electron microscope whose electrons are accelerated through 85 kilovolts, and they are telling us that the relativistic formulas should be used. Okay. So now, how do we determine the resolution of a microscope? Well, that's dictated by the wavelength of the light that we're using. So the same thing happens for an electron microscope. The electrons in an electron microscope are accelerated through a certain potential that leads to a certain wavelength for these electrons, the Broglie wavelength. Okay. So this is number 43. We have electrons that go accelerated through 85 kilovolts. Kilovolts, and they're asking for the theoretical limit of resolution, so they're essentially asking for the wavelength of these electrons. Okay? So this is, as I said, given by the Broglie relation. So to do this, we need to calculate the momentum of the electrons, and they are telling us to use the relativistic formulae. So this is going to look like h over gamma mv. All right, something like that. Maybe not necessarily this, but we need to have some gamma. So yeah, actually, this is not a good way to obtain this. So we are told that the electrons move through a potential difference of 85 kilovolts. So they're going to gain a kinetic energy of 85 kilo electron volts, right? Because as you move one electron through a potential difference of 1 volt, it gains a kinetic energy of 1 electron volt. That's the definition of electron volt, actually. Right, so the kinetic energy of the electrons is going to be 85 keV. Right, this is something we know, and we combine these, and how do you find the momentum? So I think the easier way here is using E square is P square C square plus M square C to the 4 formula, because we know that E is actually just the kinetic energy plus mc squared. So this E square is going to become kinetic energy squared plus m squared c to the 4 plus 2 kinetic energy mc squared. Right, so this drops out, and we have p squared c squared is equal to something. So p times c is going to be, ke squared plus 2ke mc squared to a half. Right, and I know everything here. So the kinetic energy is 85 keV, mc squared is 0.511 MeV, and I can calculate this number, and I get the momentum and put it there. And it is, I think it's convenient to write this as hc over pc. So we calculate the pc value directly, and this hc is 1240 nanometer electron volt. Okay, something we used for photons, it's also useful for electrons, it turns out. And so you write everything here in electron volts, and then when you divide this out, you're going to get something in nanometers, right? Which is an appropriate scale for the electron microscope resolution. It looks at nanometer scale. Okay, but I'm not going to actually carry out the calculation here. All right. So problem 50 is calculate the Broglie wavelength of an electron in the TV picture tube if it's accelerated by 33,000 volts. Is it relativistic? How does its wavelength compare to the size of the neck of the tube, typically 5 centimeters? Do we have to worry about diffraction problems blurring our picture on the screen? I mean, the last one I can answer no, because I'm actually old enough to have seen these tube televisions. You would never notice any diffraction problems. Though of course it's possible that they made some correction, right? So I shouldn't rely on that experience. Anyway, so let's take a look at this problem. Again, it's kind of similar. The electrons are accelerated through some potential difference. They gain some energy, and that leads to some wave effects, which are presented by the Broglie formula. So these two problems are very similar to each other, kind of showing different aspects. Okay, so this is problem 50. Excuse me. Let me see this. So here our potential difference is 33,000 volts. That would lead to a kinetic energy of 33,000 electron volts. Okay. Is it relativistic? So how does this compare to mc square, which is 0.511 MeV? So if you write this down, 511, right? So I will say this is relativistic, right? I mean, 33 part in 500. This is way over than a few percent. So yeah, I would say this is relativistic. Yes. How does the wavelength compare to the side neck of the tube, typically 5 centimeters? So the wavelength is h over p. Again, we can use this formula. This is hc by, let me see if I can remember it, q squared plus 2 ke mc square. Did I calculate this actually? Yeah, I did. And this gives an answer of 0.0066 nanometers. By the way, is this? I wrote something different here. Yeah. Anyway, it doesn't matter. Doesn't really matter. So this is way smaller than 5 centimeters. So you wouldn't expect any diffraction effects. Yeah. So I don't see how diffraction will be relevant. So there won't be any blurring on our picture because of diffraction. Okay. So that's all I want to say here. Next problem is problem 92. A light of wavelength 424 nanometer falls on a metal which is a work function of 2.28 electron volts. How much voltage should be applied to bring the current to zero? What is the maximum speed of the emitted electrons? What's the de Broglie wavelength of these electrons? So this is kind of a mixture of a couple things, and this is actually what you would expect. You should expect in the upcoming exam. That I'm not going to ask a question directly about the de Broglie wavelength, not a computational question anyway, but you can just ask it in relation to another aspect, like the Compton effect or the photoelectric effect. Those can very easily include the de Broglie wavelength calculation. So this is let me see, 92. So again, we have this surface. We have these photons coming in, and it just ejects these electrons with the photoelectric effect. The wavelength of the photon is 424 nanometers. And the work function is 202.28. 200. That will be some metal. How much voltage should be applied to bring the current to zero? Okay, so these electrons, they actually try to fly to the other electrode, and we can apply reverse potential between this metal, this electrode, and the other one that's supposed to receive the electrons. And if we apply enough reverse potential, then the electrons leaving this metal with a certain kinetic energy will not be able to climb that potential well. This is the idea. Okay, so they have some kinetic energy, so they can climb, they can go over some potential, and if it's a reverse potential, they have to spend this kinetic energy to move forward, and beyond some value of reverse voltage, they won't be able to actually reach there. They won't be able to climb that potential well. So how do we calculate this? Well, when light of this wavelength falls on, it actually deposits its energy. Every photon deposits its energy to an electron, and that electron spends part of that energy to the work function, and the rest of the energy of the photon is available as kinetic energy. Right, so if we calculate the kinetic energy in electron volts, then we can very easily say that over this much voltage we are going to spend all this kinetic energy, and we won't be able to climb the potential well beyond this potential difference. Okay, so this is part A. So the energy of the photon is hc over lambda. This is 1240 by excuse me, 424 electron volts. Did I calculate this? This is 92. Yeah, this comes to 2.9245 electron volts, and so this is above the work function, right? So the electrons will be able to leave the surface. This is enough for them to move from the surface, and they're going to start their journey with the difference between an energy, kinetic energy, the difference between these two numbers, right? So the kinetic energy of the electrons is going to be E photon minus the work function, and did I calculate that? This is 0.644 electron volts. Therefore, a required potential to cut current is 0.644 volts, right? 6445. I don't know why I wrote it this way, but yeah, doesn't matter. Okay, so for part B, what are they asking? What is the maximum speed of the emitted electrons? So the maximum speed of the emitted electrons is this, right? When they are emitted from the surface, before they start climbing the potential well, they are going to have this much energy, and this is the maximum available. There could be other issues, like they could be coming from deeper, from the metal. They could undergo some collisions and lose energy that way. But this is, if they're coming just from the surface, the work function by definition is the only thing that they lose. So this is the energy available to them. So we need to calculate this 0.644 electron volts is a half mv squared, and I can very comfortably, very safely use the non-relativistic formulas, because this energy is much less than the rest energy, okay, which is half MeV. So 511,000 electron volts. So you can use the non-relativistic formula, and yeah, you need to make some conversions, I guess. You can of course write this as Vc, so you can make this mc square and make this v square by c square. Then you have something in electron volts on the other side as well, and you can calculate v over c. That might be the simplest way to calculate this. Okay, so for part C, what do we have? Do I have a value here? Not really. What's the de Broglie wavelength of these electrons? This is going to be h over p, and again this could be just mv, right? And yeah, if you calculated the kinetic energy, then you can if you calculated the speed, then you can easily calculate the momentum this way. Can we make this a bit easier? So as I said, you can write this as a half mc square v by c square. So you would have the value of V by C. So you can write this as HC over M C square V by C. Right? Now these are things that you know. This is 1240 electron volt nanometers. This is half MeV, and this VC is something you calculated from the first part. Yeah. So to simplify the algebra, you could do it this way. Though it's fine if you just plug numbers in. That's also fine. There's nothing to it. Okay. So I think that's all I want to say. Thank you.